Hello student, welcome to the online lecture series. Myself Dr. S.R. Patil. I am working as assistant professor in chemistry at the S.V.K.T. Arts, Science and Commerce College, Deolali camp. Dear student, today's session for the SYBSc students and the course name is Physical and Analytical Chemistry. This course is included in your syllabus for third semester. In this course, there are two sections. First sections for the physical chemistry and the second section for the analytical chemistry. And today we discuss the section second, analytical chemistry. In this section, the today's topic is the volumetric analysis. Dear student, this is our second session on this topic, volumetric analysis. Before starting today's session, we take quick recap of our previous session. In the previous session, we had already discussed the introductory part about the volumetric analysis, the definition of volumetric analysis, along with we had also discussed the classification of reactions in volumetric analysis. Further, in the previous session, we had discussed about the standard solutions. What is meant by standard solution? The definition. Along with standard solution, we had also discussed another term, that is the molarity. Then further, we had also discussed some different terms which are used in the volumetric analysis. In that, we had discussed the equivalence, normalities and the oxidation number. So, all these points we had covered in our previous session. Now, the session agenda for today's lecture is the preparation of standard solutions. In today's session, we have discussed how to prepare the standard solution, what is meant by standard solution. Then we have also covered the next point in today's session is the primary standard substances and the secondary standard substances, their definitions and their examples. Then further, we have discussed the neutralization titration. All these points we have covered it in this today's session. So, our first point of this session. Then further, the learning objective of today's session. By this session, students are able to define the standard solutions, primary standard substances, secondary standard substances, then acid-base indicators. By this session, students are also able to explain why indicator shows color change and pH range of color change for the indicators. The next objective of today's session for the student to understand how to prepare the standard solutions and perform the standardization of solution. How to standardize the solution we have learned in this today's session. So, our first point is the preparation of standard solution. For the preparation of standard solutions, there are two methods. First is the direct method and second one is the indirect method. First we discuss direct method. In that, a standard solution water and diluting to an accurately known volume in a volumetric flask. Generally, a solution of definite normality is prepared. For example, 0.1 normal solution of K2Cr2O7 is prepared. Okay. For that, we know that the equivalent weight of K2Cr2O7 is 49. So, this direct method is used for the preparing the standard solutions of substances which can be obtained in a highly pure state. Example of this is the sodium carbonate, sodium oxalate, sodium chloride, potassium dichromate and the potassium iodates. Okay. So this is the first method, direct method. Next method is the indirect method. In that, when the reagent or substance cannot be obtained in highly pure state, then the solution of the reagent is first prepared, okay, to give the approximately desired normality. Then this solution is used, or this solution is titrated against a solution of known concentration, and exact normality of the solution can be determined. So this process of determining the concentrations of a solution by titrating it against a solution of a substances of a known concentration is called as standardization. Once again, I repeat the definition of standardization. The above process of determining the concentration of a solution by titrating it against a solution of a substance of a known concentration. Okay, that is a standard solution, and the process is known as standardization. This indirect method is used for the preparation of solutions of acids like HCl, HNO3, H2SO4, etc. and the substances like KMNO4, Na2S2O3 and KCN. Since the sodium hydroxide NaOH is not sufficiently pure to prepare a standard solution directly, okay, so it is standardized by titrating with a primary standard acid such as the potassium hydrogen phthalate. Then second point of today's session is the primary standard substances and secondary standard substances. First we discuss about the primary standard substances. We know that a substance available in a pure form or in a pure state of a known composition, okay, which is used to standardize other solution is known as a primary standard substance. Once again, I repeat the definition of primary standard substance. In that, a substances available in a pure form or in a pure state of a known composition and which is used to standardize other solution is known as a primary standard substances. These primary standard substances should fulfill some requirements. In that, first requirement for the primary standard substance is it should be nearly 100% pure. Okay, purity is most important, and impurity of in order of 0.01 to 0.02% is tolerable. Okay, this is the tolerable limit of that substance for the purity. If it is accurately known, we have to accurately know the impurities. Next important requirement for the primary standard is it should be stable at all the time at a room temperature. The primary standard is always dried before weighing. So that's most important requirement for the primary standard substance. It should be stable at the all time at room temperature. Next important requirement for the primary standard substances is it should be readily available at moderate cost, because cost is most important. Another important requirement of primary standard is it should be readily soluble in water under the conditions in which it is used. Solubility is most important. Then another important requirement for the primary standard substances are it should have a high formula weight. Okay, and this is because the relative error in weighing decreases with increasing formula weight. Therefore, it's require a high formula weight. Another important requirement for the primary standard substances is it should not be hygroscopic or efflorescent. Okay, these are some requirements for the primary standard substance. We know that it is very difficult to get the substances which are fulfill all these above conditions, all these above requirements. Okay, and therefore the substances having most of these requirements are generally used as a primary standard substances. So the substances commonly used as a primary standard in a various type of reactions are very limited in a number. Okay, so these some substances are listed here. In the acid-base reaction, we can use sodium carbonate, potassium hydrogen phthalate, benzoic acid, borax, etc. In the redox reaction, we can use sodium oxalate, potassium dichromate, potassium bromate, and the potassium iodate. And in the precipitation reaction or in the complex forming reaction, we can use silver nitrate, sodium chloride, potassium chloride as a primary standard substances. Okay, these are some primary standard substances. Next point is the secondary standard substances. In that, a solution having exact concentration of which has already been determined by titrating it against the primary standard solution and which can be used as a titrant in a titrometric analysis or in a volumetric analysis is known as a secondary standard solutions. Okay, and the substances is called as the secondary standard substances. Once again, I repeat the secondary standard substance definition. In that, a solution having exact concentration which have already been determined by a titration against the primary standard solution. Okay, and which can be used as a titrant in the volumetric analysis or in a titrometric analysis. Such a solution is known as a secondary standard solution, and the substances is called as the secondary standard substances. These secondary standard solutions may be used for the standardization of other solutions. For example, if a standardized NaOH solution is available, then HCl can be standardized by titrating a known volume of it with the NaOH, HCl with the NaOH. This is example for the secondary standard substance. Then the endpoint is sharp and the titration is rapid. The NaOH solution is thus a secondary standard solution. Some substances like NaOH, Na2S2O3, KMnO4, FeSO4 are used as a secondary standard substances during the volumetric analysis. Next important point of today's session is the type of volumetric analysis method. We know that there are 4 types of volumetric analysis method. First type is a neutralization titration. Second is the complexometric titration. Third one is the redox titration. And fourth type for the volumetric analysis method is the precipitation titration. Okay. So in today's session, we discuss a first type, neutralization titration. In that, we know that the fact is that the acids and bases neutralize each other has been used to determine them. And the equivalence points or the cytometric or the theoretical endpoint of this titration can be determined with the help of substances called as the neutralization indicators or acid-base indicator. So next important point about the indicator is the theory of indicator. What is mean by indicator? Okay, so we discuss some theory about the indicators. So most of the visual indicators used in acid-base titration are themselves weak acid or bases. The acid-base indicators are characterized by their different colors in acidic and alkaline media. Okay, so an indicator which is colorless in one medium and colored in another medium is called as a one color indicator. Important term, one color indicator. Okay, the indicator which is colorless in one medium and colored in another medium, which is called as a one color indicator. Okay, like one color indicator, there is a next term two color indicator. Okay, an indicator which has a definite but different visual colors in a different media is called as a two color indicator. So very simple. From name itself we can clarify the term one color indicator and two color indicator. Okay, so we take the example the phenolphthalein, which is colorless in acidic medium and red color in an alkaline medium. So phenolphthalein is an example of one color indicator. Okay, while the methyl red, which is pink in acidic medium and shows yellow color in alkaline medium, it is an example of two color indicator. One color indicator is the phenolphthalein because which is a colorless in acidic medium and phenolphthalein shows a red color in alkaline medium, therefore it is example of one color indicator. On the other side, methyl red, which shows a pink color in acidic medium while yellow color in alkaline medium, and therefore it is example of methyl red is example of two color indicator. These color changes are associated with the ionization of the indicator. Okay, why this color change is happen? Because this color change is associated with the ionization of indicator, and the colors of molecular form and the ionic form, that means the acid form and base form of indicator are different. Okay, for example, we see the equation H ion, that is the molecular form of or acid form of indicator H ion. On dissociation or on ionization, it gives H plus plus ion minus, which is a ionic form or a base form of indicator. Let us consider an acid base indicator H ion. Ion stands for indicator. So it ionizes reversibly in aqueous medium as a H ion. On ionization it gives H plus plus ion minus. Okay, when we apply the law of mass action, it gives K indicator is equal to concentration of H plus ion into concentration of ion minus ion divided by concentration of H ion. Okay, so here K indicator is called as the apparent indicator constant. Okay, when we rearrange this equation, we get the concentration of H plus ion is equal to K indicator into concentration of H ion divided by concentration of ion minus ion. Okay, therefore is equal to K indicator into concentration of acid form divided by concentration of base form. Therefore minus log concentration of H plus ion is equal to minus log of K indicator minus log of concentration of acid form divided by concentration of base form. Okay, therefore pH is equal to K indicator minus log of concentration of acid form divided by concentration of base form. This is the final equation. So the color of the indicator, which depends upon the ratio of the concentration of ionized form and unionized form, that means the base form and acid form, okay, is directly related to the hydrogen ion concentration. So the ratio of the concentration of acid form and base form should be more than 10 to observe the color of the acid form of the indicator distinctly. Once again I repeat, the ratio of the concentration of acid form and base form should be more than 10 to observe the color of the acid form of the indicator distinctly. Okay, There is another equation or another sentence in that the ratio of concentration of base form and acid form should be more than 10 to observe the color of the base form of the indicator distinctly. Okay. From above these two equations, first for the acid form and second for the base form. So, from these two equations it is clear that the change in color of indicator will be clear when the pH of the solution is 1 unit lower or higher than the pK indicator value. Okay. Once again I repeat, because this is most important term regarding to color change of indicator, and by observing these two equations it is clear that the change in color of the indicator will be clear when the pH of the solution is 1 unit lower or higher than the pK indicator value. Okay. So, this color change interval in a pH unit is called as the transition range of indicator. Okay. This color change interval in a pH unit is called as a transition range of indicator. There is another term, transition range of the indicator. Thus, the condition for sharp change in color of the indicator during the titration is, what is the condition? The pH is equal to pK indicator plus minus 1. Okay, this is the most important equation. So, this equation shows that the transition range of an indicator is usually 2 pH unit. pH is equal to pK indicator plus minus 1. And this equation shows that the transition range of an indicator is usually 2 pH units. This is the most important equation. In the transition range, the indicator will be shows a mixed color. Remember that in the transition range, the indicator will shows a mixed color. The sharpness of the color change depending also on the absorption maxima. Okay, absorption maxima and molar absorptivity of the different species of the indicator. Okay, so remember that the sharpness of the change in color of indicator or during the titration is depending upon the absorption maxima and the molar absorptivity of a different species of the indicator. Due to these factors, the transition range of the indicator is sometimes less or more than 2 pH units. Okay. For example, the transition range of methyl orange and bromothymol blue, these are the names of indicators, methyl orange and bromothymol blue. Okay. We have considered about the transition range of these two indicators, and we say that the transition range of this indicator is less than 2, while transition range of methyl red and nitromines is more than 2 pH units. These are the examples of one less than 2 pH unit transition range and more than 2 pH unit transition range indicator. Within the transition range, the indicator appears to change from one color to another. It's very simple. Transition range, we already discussed the definition of transition range. Indicator converts one to another color. The change is gradual since it depends upon the ratio of the concentration of the two color forms, that is the acid form and base form. When the pH of the solution is equal to the apparent indicator constant pK indicator, then the ratio becomes 1. Okay, and the indicator has a color due to mixture of equal concentrations of acid and base form. Once again I repeat, when the pH of the solution is equal to the apparent indicator constant pK indicator, then the ratio becomes 1 and the indicator has a color due to a mixture of equal concentration of acid and base form. Okay, and this is sometime called as, or this term is known as a middle tint of the indicator. Okay, and this applies strictly only if the two colors are of equal intensity. Middle tint, there is another concept of the indicator. If one form is more intensely colored than the other, or if the eyes is more sensitive to one color than the other. Okay, we can apply when the two colors are equal intensity, middle tint of the indicator. Then the middle tint will be slightly displaced along the range of the indicator, or the ratio of acid form to base form may not be 10 to 1 or 1 to 10. Once again I repeat, when the middle tint will be slightly displaced along the range of the indicator, or the ratio of acid form to base form may be 10 to 1 or 1 to 10. This is about the theory of indicators. Next point of today's session is the neutralization curve, or we can say the titration curves. It is a plot of change in a concentration of H plus ions, or pH, as a function of the titrant. That means the solution which is filled in a burette, titrant. Okay, the titrant added is known as a neutralization curve or a titration curve. Once again I repeat the definition of neutralization curve. A plot of the change in the concentration of H plus ions or pH as the function of the titrant added is known as the neutralization curve or the titration curve. It is a simple curve that the change in the pH near the equivalence point is of a great importance, because it enables us to select the indicator. Why it is important? Because it enables us to select an indicator which will give the smallest titration error. Okay, in a volumetric titration, using a visual indicators forming a terms are often used, which must be properly understood. There are different terms during the volumetric titration or during the titrometric analysis using a visual indicators. We discuss all these terms one by one. The first term is the endpoint. We know that endpoint because in our previous session we already discussed the definition of endpoint. Okay, what is endpoint? The point at which the indicator changes its color during a titration is called as the endpoint of the titration. Okay, so the indicator changes its color when it passes through its transition range. We already discussed about the transition range. For example, the indicator methyl orange has a transition range 3.1 to 4.4 pH unit. During titration, as long as the pH of the solution is below 3.1, then the indicator shows a pink color. When the pH of solution becomes more than 4.4, then it shows a yellow color. Okay, and in between pH 3.1 and 4.4, it shows a mixture of color. That means a different shades of orange color. Okay, when we use these methyl orange as an indicator during the titration, the color changes from pink to yellow, and this is the end point of our titration, pink to yellow, by using the methyl orange as an indicator. Next important term in the volumetric analysis is the equivalence point. What is the equivalence point? The point at which exactly equivalent quantity of acid and base are added to one another in a titration is called the equivalence point of the titration. Okay, equivalence quantity, we know that gram equivalents or in a milligram equivalents. So once again I repeat the definition of equivalence point. The point at which exact equivalent quantities of acid and base are added to one another in a titration is called as the equivalence point of the titration. For example, when 25 ml of 0.1 normal HCl is titrated against the standard 0.1 normal NaOH solution. Okay, we take 2.5 milliequivalent of titer HCl in the conical flask. That means 0.1 into 25. Okay, therefore it is a 2.5 milliequivalent. Okay, when we add 2.5 milliequivalents of the base NaOH to it, the equivalence point is said to be reached. Okay, we have to take 2.5 milliequivalents of titer HCl in one conical flask, and then in that we have to add 2.5 milliequivalents of the base NaOH. Okay, then the equivalence point is said to be reached. And this point is obtained when the 25 ml of 0.1 normal NaOH are added to the titer. Okay, and the equivalence point can be calculated theoretically. That means even without doing the titration. For example, if 25 ml of 0.2 normal H2SO4 are titrated against a 0.1 normal NaOH solution, then the equivalence point will be obtained after adding a 50 ml NaOH solution. This is the equivalence point. Next term is the neutralization point. What is the neutralization point? The point at which pH of solution becomes exactly 7 during the titration is called as the neutralization point of titration. It's very simple. The point at which pH of the solution becomes exactly 7 during the titration, which is called as a neutralization point of titration. We take one example. The titration of strong acid and strong base. Here we use a HCl as a strong acid and NaOH as a strong base. Then the pH becomes 7 when exactly equivalent quantities of acid and base are reacted with one another. This is the example of neutralization point. Another term is the suitable indicators. We know that during the titrometric analysis we have to require a suitable indicator. Then which is the suitable indicator? The indicator which shows a color change during the pH change taking place at the equivalence point is called as the suitable indicator. Once again I repeat, the indicator which shows a color change during the pH change taking place at the equivalence point is called as a suitable indicator. We consider one example. In a titration of strong acid and strong base, the pH changes at the equivalence point is nearly 3 to 10 pH unit during the strong acid and strong base. Then the indicators, methyl orange, the range is 3.1 to 4.4. Methyl red having range is 4.2 to 6.3, and the bromothymol blue having a range 6.0 to 7.6, and the phenolphthalein 8.3 to 10 pH unit. Okay, have their transition range between the 3 and 10 pH unit. Okay, these are the some indicators having a range, their transition range between the 3 and 10 pH unit. First we take example of methyl orange having a pH range 3.1 to 4.4. Second indicator is a methyl red having a range 4.2 to 6.3, and the range of bromothymol blue is a 6.0 to 7.6, and well known and popular indicator phenolphthalein having a range 8.3 to 10. Okay, these are the transition ranges between the 3 to 10 pH units of different indicators. These indicators can show the color change during the 3 and 10 pH units. Okay, so they are the suitable indicators for the titration. Okay, they show the color changes between the 3 to 10 pH units, and therefore they are suitable indicators for the titration. Next term is the best indicator. Which one is the best indicator? Okay, in that a suitable indicator which has its transition range around the pH at the equivalence point is called as the best indicator. Which indicator we can say the best indicator? A suitable indicator which has its transition range around the pH at the equivalence point is called as the best indicator. Example for the best indicator: in titration of strong acid and strong base, or titration of strong base and strong acids. Okay, example is NaOH and CH3COH. The pH at the equivalence point is 8.73. Okay, so out of the suitable indicators, the phenolphthalein has its transition range is a 8.3 to 10. Therefore, it's around pH 8.73. So best indicator is a phenolphthalein for this titration. Okay, so this all about the today's session. Now there is one assignment for the student on the basis of this session. In the assignment, you have to solve first question to define the different terms. In that, you have to define the standard solution, primary standard, secondary standard, standardization, neutralization curve, suitable indicator, and the best indicator. All these terms we have discussed in today's session. We have to define this term. There is another one question in the assignment, which is a derive the relation pH is equal to pK indicator plus minus 1 for the indicator. Okay, you have to derive this relation. So, dear student, solve this assignment and send or upload this assignment on your Google Classroom for the SYBSC class. Dear student, in the next lecture, we will discuss 4 different types of titration curves. We know that the 4 types of titration curve. In that, we will discuss a strong acid and strong base curve, then a weak acid and strong base curve, then we will discuss the titration curve for a strong acid and weak base, along with a titration curve of a weak acid and weak base. All these types of titration curves we will discuss in our next session. So, dear student, thank you very much for this session. Thank you.